I particularly want to welcome folks who are in the Aspen community and thank the Aspen Center for Physics for hosting this public talk. I'm Chanda Prescott-Weinstein. I am an organizer of the Rainbows of Dark Sectors conference that is happening. It happened last week. I'm wrapping up tomorrow, and this public talk is part of our conference activities. And I'm going to be introducing our speaker tonight. I'm pretty excited about this. So I don't want to take up too much of your time, so I'm just going to go ahead and get started. So it's my pleasure to introduce this evening's speaker, Dr. Gopolang Mohlabeng. Dr. Mohlabeng is currently a postdoctoral fellow at the McDonald Institute of Queen's University in Canada. And starting this fall, he will be starting a prestigious Chancellor's Advanced Postdoctoral Fellowship in Physics at the University of California at Irvine. Dr. Mohlabeng's career has traversed diverse geographies. He's originally from South Africa. He earned bachelor's degrees in physics and astronomy from the University of Pretoria and the University of Cape Town. He went on to win a prestigious Fulbright student fellowship and earn a master's and PhD from the University of Kansas. During his time as a graduate student, Dr. Mohlabeng was selected for a prestigious program as a visiting student at the Department of Energy's Fermi National Lab. And his dissertation, which was titled Charting the Unknown, A Hunt in the Dark, won the Marnie and Bill Argersinger Outstanding Doctoral Dissertation Prize. Today, Dr. Mohlabeng is an expert on dark matter, a subject he explores through theoretical, computational, and data-driven analyses. He has such impressive breadth. I hope you all will be able to appreciate it in his talk tonight. And in addition to his research in dark matter, Dr. Mohlabeng is an advocate for broadening participation in and access to physics and astronomy, particularly among communities which have been traditionally excluded from South African and North American professional circles and beyond. So I'm really excited tonight. Dr. Mohlabeng will talk to us about his work, and the title of his talk is Unraveling the Mysteries of the Dark Universe. So Hopi, please go ahead and share your screen, and whenever you're ready to get started, we're excited to hear from you.
Can you see my screen?
Yes, so you just want to hit play. And for the audience, there will be time for questions at the end. Go for it.
Okay. Well, thank you for that very broad introduction, and thank you to the organizing committee of the conference for recommending me to give this talk. I also want to thank the hosts, the Aspen Center for Physics, also for making this talk possible. So today I'm going to be telling you about unraveling the mysteries of the dark universe. Before I continue, is there any way that I can remove this? I don't know if you can see this is.
It's not blocking your slides, so you're fine.
Okay. So before I start my talks, I usually like to introduce myself. But as you can hear, well, I've just been introduced very well. But I like to say where my name comes from. So it's probably an unusual name for many of you. So my name is pronounced Gopolang with a hard, almost like a hard H. In my native language of Sotho, it means remember. And as you can see, it's long, and most people never really remember it. So I just ask people to call me Gopi. But then actually at home, my family, I'm called Hope. So let's continue. Okay. So before I start this talk, I want to first do an important recognition. So Queen's University is situated on the traditional territory of the Anishinaabe and Haudenosaunee nations. And as an invited guest, I am very privileged to be able to learn, collaborate, and live on this land that is not mine. I do this land acknowledgement also to recognize the people who have worked very, very hard before me to get to this point that we can have these sort of acknowledgements. And so I want to first ask the question, how big is our universe? And to answer this question, I'm going to play a short video. So please bear with me. Now in this short video, I would like you to pay attention to one thing. I would like you to pay attention to the scale here. So this scale shows a person just lounging in the sun. Sorry, I'll start speaking before I press the button. It shows a person lounging in the sun and the picnic table, so it's near a restaurant. One reference point that I would like to point you to is that 1 light year has about 9 trillion kilometers. And for those of you who may be having some bandwidth issues, here's a link to the YouTube video so you can watch it at your own leisure. So this video is basically showing us, tries to show us the scale of the universe. So as we zoom out from that picnic table and the person lying in the sun, we see basically the scale of the entire Earth. So this shows the west coast of North America. Here we see the United States. We see the Earth. And again, please pay attention to that scale. So this is the scale of the Earth-Moon system. And as we keep zooming out and more and more and more, we get to the scale of the solar system. So now we see basically how large our solar system is. As we keep zooming out, we see even more and more structure in our region of space. So this is at the point where we reached 1 light year. Okay? And I will explain what a light year is in a bit. So we keep zooming out. And now we actually see the scale of our galaxy. And we can see our position in the galaxy, our Milky Way galaxy. So, but then we keep going, just keep zooming out. And now we see the scale of different galaxies. And beyond that, structures and filaments as we zoom out, like basically going to the edges of our universe. So now pay attention to this. We've reached the edge of the universe, it's about 10 billion light years wide. So we're just going to zoom back in to that third rock from the sun, which is our home Earth. Now, the exercise, the main point of this exercise was to basically show you how large our universe is. So it takes light, basically 13.6 billion years to move from one edge of the galaxy to the next edge of the galaxy. So a light year literally means the amount of distance light travels in one year. And so there are billions and billions. So we saw in this video that there are billions and billions of stars and galaxies and structure and gas and all these wonderful, beautiful pictures. So for those of you who are in Aspen, you might know the U Trail. So if you're brave on an evening, you can go up the U Trail if you're not afraid of bears like I am. You can go take a cheap telescope, go up the U Trail and go to Overlook Pass. And you may be able to see these kinds of pictures because you're above the light pollution from the city. And so you may ask yourself, well, surely this is all the universe is made of. But we know that this is actually not true. It turns out that all that stuff, all those billions and billions of stars and galaxies and clusters, actually make up only about 5% of our entire universe. This, when I first heard this, I was flabbergasted. I was like, no, surely you're lying. This was when I first took my my first course in astronomy. And this really made me want to learn more about our universe. There's so much mystery in our universe that we don't know about. And a lot of this mystery is in the 95% of our universe that we don't know about, which is dark. And it's at this point that the nerd in me comes out, and I couldn't resist but put a reference to Star Wars. So come join me and let's go to the dark side and explore the dark side of our universe. So about 26 to 27% of our universe is in an unknown form of material we call dark matter. We know very little about this. All we know about it is basically that it exists. And the rest of our universe is in an even more unknown entity we simply call dark energy, because we have absolutely no idea what it is. Okay. And so, as Dr. Prescott Weinstein mentioned before, there's a current workshop that's happening currently called the Rainbow for All Parts of this. And here, particle and astrophysicists are very excited and wake up every morning, have our coffee, and we really, really want to answer these two questions. What is dark matter, and how do we go about finding it? And so, today I'm going to give you a sort of cosmic menu. I just gave you an appetizer. So the main course today is going to be, how do we know that dark matter exists? So I'm going to go through what galaxies tell us about dark matter, what classes of galaxies tell us about dark matter, and what a universe in its infancy, just after it was born, after the Big Bang, whatever that is, after that happened, what the universe tells us about dark matter and structure in our universe. And I want to put it to you that all of these are covered by gravity. Besides the gravitational interactions that this has, we really don't know anything else about dark matter at those scales. And then I'm going to talk about what we do or don't know about dark matter, what dark matter could be, and what it definitely is not. And also, how do we go about finding dark matter? So we go and look for dark matter in the sky, we look in our laboratories, and we also look deep underground. So before I start this dark matter journey, I'd just like to start at our solar system. And I have to now at this point catch myself. If I end up talking too fast, please interrupt me and tell me to slow down. I end up sometimes rambling a little bit. But let's start at the scale of our solar system. So gravity tells us a lot about our universe. In our solar system, gravity tells us, we know that the sun has a gravitational field that forces planets to orbit around it. And this leads us to Newton's law of gravity that tells us that planets that are closest to the sun move faster than, or orbit the sun faster than planets that are further away from the sun. And so using the velocities or the speeds of these planets as they rotate around the sun, we're able to measure the mass of the sun and in turn the mass of the solar system. So we get that the mass is about 1.9 trillion kilograms. And in effect, the mass of the solar system, once you put in all the planets and all these other comets and dust and everything, you get about 2 trillion kilograms. So basically, the solar system is dominated by the mass of the sun. Now, imagine for a second that the sun was still there, but now it becomes invisible. There's no light that is being emitted. So we don't have day, we don't have night. If any of you remember that movie 30 Days of Night, this case would be the same, but without the black clouds. And so we would still be able to measure the mass of the entire solar system and infer that the mass of whatever is in the center that's causing this gravitational pull of these planets is still about 1.9 trillion kilograms. And so we use this notion of planets moving around the solar system to much larger scales. So we start with scales of a galaxy. And basically, scientists going back to the 1800s use this exact idea of measuring smaller objects that are revolving around the galaxy to kind of try to measure the whole mass of the entire galaxy. So this started with, in 1884 with Lord Kelvin, who estimated that there was unseen mass in our galaxy by measuring the rate that stars move around the galactic center. And it was in 1906, learning from the work of Lord Kelvin, that Henry Poincaré first called this unobserved matter. He referred to it as dark matter. Now, the trail takes us then to 1933, when Fritz Zwicky used a similar type of notion, but only now at larger scales of clusters of galaxies. And he was looking now, instead of at the velocities of stars, he was now looking at the velocities of galaxies as they move in the galaxy cluster. And he looked at a specific cluster of galaxies called the Coma cluster, where he calculated that there was 400 times more mass than what he could observe when looking through the telescope. He called this unseen matter Dunkumoteri, which is a black material translated in German. And obviously, there was some controversy with this, and people didn't really believe that. How can you say that really there is no unobserved matter or black matter? It was only in the late 1970s or early 1980s that the dark matter game completely changed. When Vera Rubin, who was actually the first person to measure star speeds at very, very high precision, when she measured these using a spectrograph that she and her collaborators invented or came up with. And what they found was that just as in our solar system, when we move away from the center of this rotating system of the sun, we see that the speeds should actually keep dropping. So we expect the same in our galaxy. Right? Newton's laws tell us that as I move away from the center of the galaxy further out, the speed should increase because there's a lot more mass over here. And when there is less and less mass, the speed should decrease. What Vera Rubin and the collaborators found was actually, no, that's not true. What they observed was that the speeds increase and they stay the same. Now, this is a discrepancy in our logic. Newton's laws tell us this. So what are we actually seeing? So to put it in effect, if we look at a galaxy face on, what this is saying to us is that a galaxy should be rotating faster in the center than it is at the outer edges. But what they saw was it's actually rotating almost at the same rate as it is towards the center. Now, does this tell us that there is dark matter? Definitely, it does tell us that there is dark matter because there must be some unseen matter over here. Now, you want to call that dark matter? This is unfortunately, this is what we call it. It becomes this unseen documentary dark matter, invisible matter, whatever you want to do. And for her pioneering work in this field, without which we wouldn't have all this evidence that we have today. There's a very sensitive telescope that is currently being built in Chile. This is basically going to revolutionize astronomy. And it was formerly called the Large Synoptic Survey Telescope. Has now been named the Vera Rubin Observatory. And so I just made a big claim, right? That what galaxies tells me is that there is dark matter. What if my understanding of Newton's gravity is wrong? Or maybe it's not wrong, but what if our understanding of the galaxies is completely incorrect? People have actually thought about this, and this is what we call the modification of Newtonian dynamics. What Mond says to us is that there is no dark matter. Basically, I can take Newton's gravity and change them, Newton's law of gravity, and change it such that I fit this data at galactic scales. So now we have two opposing views. There's one that says there's some unseen matter that surrounds our galaxies. And then there's one that says, no, there's no such thing. I can just change my mathematics to fit the data as I see it. Okay. Now let's put a pin in this for a second. And I'm going to try to convince you that actually dark matter exists at all scales. While this other theory doesn't make much sense while you start going to larger scales in our universe. So one of the really great things about gravity is that it not only tells us about how to calculate the masses of galaxies using stellar rotation of the speeds of stars around the galaxy, but gravity can also bend light. So how it does this is that if I have a galaxy, did I say galaxy? Gravity, yes. So if I have a galaxy that is very distant, and in front of it there's another massive object, like a cluster of galaxies. This cluster of galaxies is so massive that it is able to bend the light that is coming from this galaxy in the background. And what I see on Earth is distorted light from this distant galaxy. We call this phenomenon gravitational lensing. And how we see this in our telescopes is actually in terms of these rings, these distorted rings or image here, where this is the gravitational lens, or the object that is lensing, kind of bending this light. And this is the gravitationally lensed object. And we see enough of these images that we think that it's not an artifact of the telescope, but it actually is something physical that is really happening. And now let's again imagine, use our imaginations for a little bit, and imagine that the galaxy cluster is invisible. It's there, but it's invisible. So this light from this galaxy would actually be bent by something that we can't see. And basically, this is how we infer the existence of dark matter at scales larger than the scales of galaxies. And so the poster child for this kind of evidence is called the bullet cluster of galaxies. And you'll see in a bit why it's called the bullet cluster. So this is an image or an animation of two galaxies that were merging, that went galaxy clusters that went through each other. And this is basically called the bullet cluster of galaxies because we see this kind of resembles a bullet going through some material. And I'm sorry for the violent imagery. We see these blue regions here, and this red region actually is gas that we can see in the telescope. So if we look at this, these are photons that come into the telescope. But this region we cannot actually see. And how we know that it's there is through gravitational lensing, where the light from these distant galaxies are bent by these structures over here. Now let's go back to this comparison. And again, I don't need to make a comparison, but this is to show you that sometimes in science we need to have opposing views and try to fit with the data in order to see really what's going on in the picture. So for someone who doesn't really necessarily believe that dark matter exists, so I'm giving you dark matter and I'm giving you something else. I'm not just coming to you and preaching that dark matter exists, just believe me as I say that. Okay. And so dark matter is actually consistent with explaining the scales of clusters of galaxies. It can explain also the scale of galaxies. But modification of gravity and dynamics, can only explain the scale of galaxies, but cannot actually explain consistently the scale of clusters of galaxies. So we need MON plus something else in order to really explain this. So this inconsistency with this other theory is something that really tells us that there is something, there must be something that exists out there, kind of resembling what we think of as dark matter. Now, if you still don't believe me, let's go to even larger scales than that. Now we look at the universe in its infancy, right? Like a few seconds just after the universe was born, just after the Big Bang happened, whatever the Big Bang is. And so this picture here shows kind of random, small, very, very minute temperature fluctuations that occur after the universe was born. And as the universe expands and cools, these minute temperature fluctuations give rise to dark matter clouds. And as the universe keeps expanding, these temperature fluctuations also give rise to photons, which travel as the universe expands and they reach us today. Now the universe is expanded and cooled, and in our region of space, these photons actually have a temperature of about 3 Kelvin. We call these photons the cosmic microwave background radiation. What the cosmic microwave background radiation is, basically, it gives us a whole picture of our universe, a larger picture. It tells us how the universe looked immediately after it was born. And cosmologists have found a way to take that data from photons and turn it into a mathematical picture that allows them to understand understand the properties of our universe. And it's something we call the power spectrum, the cosmic microwave background power spectrum. So we see here, these are the data points that we actually observed from the previous satellite called the WMAP satellite. And in this power spectrum, so we plot fluctuations as a function of angular scale, because when we look outside, we look at basically, when we look at the universe, we look at basically in some angular, within some angle, right? And so the first peak basically tells us that the universe is flat. The second peak tells us how much matter there is in our galaxy, in our universe. And the third peak tells us how much dark matter there is in our universe. Now, you could say, wait a minute. I thought, if I don't believe that there's dark matter, then the third peak possibly can't come. Now, how I can try to convince you of this is to say, well, let me come up with a theory. I have two theories. One that says dark matter exists, and one that says dark matter doesn't exist. And basically, I can just modify gravity. And we see that at those very, very large scales, here, the solid line is a theory that tries to modify gravity and it says dark matter doesn't exist. And we can see that it does not fit the data at that peak at all, and even at higher peaks. And we see that dark matter fits the data very, very well at those very large scales. So I've just shown you evidence that dark matter exists at the scales of galaxies, galaxy clusters, and the largest scales in our universe. Now, I've actually only shown you three pieces of evidence that dark matter exists. There are a lot more evidences that dark matter exists. But unfortunately, this is not a talk about how dark matter exists. So I'm going to stop here today. Now, actually, interestingly, we can see these CMB photons in our appliances at home, particularly in your TV, if you have an older TV, and in FM radio. So if you switch between TV stations and between radio stations, you hear this shh noise. About 10% of that is actually CMB photons interacting inside the TV or your radio. When I found this out, I went home and I played with the TV so much, my mother had to shout at me and I had to stop. So this is really cool for me to know that this is something that happens. So why does dark matter matter? Why do I care about dark matter? Why should we care about dark matter? Well, before I tell you why you should care about dark matter, or at least why I care about dark matter, I want to tell you that Einstein's gravity, obviously, in Einstein's gravity, we have a space-time continuum, and any object that is very massive bends the space-time continuum. So if another smaller object comes within the bent continuum, it falls within and gets trapped by the gravitational potential well that is formed by this more massive object. So the prime example of this is the Earth-Moon system. The reason that the Moon orbits around the Earth is that it's trapped by the gravitational potential well that the Earth is causing. The same with the Sun and the planets in the solar system. And so in a similar way, this is how dark matter works. So dark matter is important because it shapes the universe as we know. Dark matter traps visible matter and in a gravitational potential well, and causes them to, this is how galaxies and galaxy clusters and all these structure that we see are formed. The quickest analogy that I can make is take a big rubber sheet, stretch it out, put a bowling ball, put a bowling ball in the center, and you know that you'll notice that the sheet is bent, is distorted by this bowling ball. Take marbles or ping pong balls and throw them in there. We know that they're going to go to where the dip in that sheet is. So this is our space-time, this is the dark matter, and this is the visible matter that gets trapped and forms galaxies that only in this case, in the case of dark matter is invisible. We don't actually see it, but it's there and it traps all this matter. Now in the next picture, we see two things. We see data on this side that was taken by the Sloan Digital Sky Survey and simulations. Now again, I'm sorry, I don't know why this is happening, but my computer, okay, I think this is what I actually needed to show. My computer is stopping this animation. Anyway, so simulations, in our simulations, we can see these filamentary structures. So in this region, we have dark matter over dense regions. This region is very dark matter under dense. So we can see this clumpy structures. So if we zoom into here, we see where galaxy clusters, and all the structure occurs. In principle, if you look at this data very carefully, so the Sloan Digital Sky Survey was a survey of a lot of galaxies, billions and billions of galaxies in our universe, as far out as that telescope could reach. And basically, they saw similar structure, kind of filamentary structures, where there were regions of overdensities and regions of underdensities. Again, I apologize that this animation is refuses to work. And if you zoom out, if you keep going to larger and larger scales, if you keep going to larger and larger scales, we see this this kind of those random temperature fluctuations. I'm sorry, I apologize for my setup here. Keep pressing buttons all over the place. So I hope at this point that I've convinced you that dark matter exists, and we think we understand. Cosmologists, astrophysicists, particle physicists, we think we understand for modeling and what the universe, data in our universe is telling us. So the inconvenient truth about dark matter is that if it is a particle, it must be a new particle. Whose mass we don't know. Does it have spin? We don't know. And by spin here, I don't mean like a spinning object, but I mean the intrinsic quantum mechanical properties of a particle. Does this particle decay or is it stable? Is it other than gravity? We know that this particle would have to have interaction with gravity because we saw that there is dark matter. But other than that, do we actually really know how it interacts with us? Is it an elementary particle like the electron, or is it a bound state of different particles like the proton? We don't really know. And so let me explain what I mean by particle in this case. So I'm going to show a small, another short video. So, and I want to apologize again if this is going to make you too much, but this is a human eye. So again, please pay attention to these scales. So now we're zooming in, instead of zooming out of a galaxy, now we're going to the smaller scales inside, and to get to basically the building blocks of light. So now we're looking at fractions, very small, tiny fractions of millimeters. So we're now looking at a DNA strand, a group of atoms, and we're zooming into one particular atom. You see the orbitals of the electrons. We go deeper into this atom, and we get to the scale of the atomic nucleus. The atomic nucleus is made up of a neutron and a proton, and those guys are made up of, the neutron and the proton are also made up of even smaller particles we call quarks. This brings us to the building blocks of life, which is the standard model of particle physics. What the standard model tells us, basically, it's a theory that tries to classify all the particles that make us up, all the visible matter particles in the universe, basically that 5% of our universe. And so it's classified into fermions, which are quarks, leptons, these are the matter particles, and the force carrier particles. And this special particle here called the Higgs boson. Now, we remember that the four fundamental forces of nature. There's gravity, which we saw is very important in our universe. There's electromagnetism. There is the weak force and the strong force. The strong force is responsible for why I can pinch myself at this point and still not disintegrate and go back together. So it holds atoms nuclei together. The weak force is responsible for life because of radioactive decay. And the photon that carries the electromagnetic force is very important in the sense that we can see each other at this point. Right? Well, I see my laptop, you see your computer, and there's quanta that is being transported between, and you can hear me as well. This is all because of this photon. Now, bear in mind that I've only classified these particles, this standard model, as if it was like a periodic table. And I actually haven't really shown you how all these particles interact. So allow me to burn this picture of the standard model for 1 second and show you a more interactive picture of the standard model, which basically forms that 5% of the universe that we see. And so here, the strong force interacts with the quarks that form protons and neutrons that form us, basically. Then we have the electrons, which we know very well. They have the heavier partners, and then these lighter particles, known as neutrinos. The Higgs boson interacts with all these particles except the gluon, photon, and neutrino because it gives mass to all these particles. We know that the gluon and the photons are massless, but the neutrinos actually don't get their mass from the Standard Model. So that's another question, a fundamental question of physics, is where do the neutrinos get their masses from? At this stage, the Standard Model is complete. We predicted all these particles and we built experiments and went and found all those particles. The latest was to be found was the Higgs boson at the Large Hadron Collider. So we know that dark matter is not part of the Standard Model of particle physics. So what could dark matter be? Well, it's unfortunate or fortunate to say that there is a vast range of possibilities of what dark matter could be. Some of us have maybe heard about weakly interacting massive particles, which have a mass between the proton mass and 10,000 times the proton mass. There are particles whose mass lie between the electron mass and the proton mass, which we call sub-GeV particles. The reason we call these sub-GeV dark matter particles is because the proton mass is almost at a GeV, and they have the masses just below GeV mass. I won't go into what really GeV is, just a unit of energy and mass that we use, just because of our reasons. There's also particles that are ultralight, which have trillions of fractions of the mass of the electron. And if you've heard of axions, axions fall into this class of particles. Now, going to the opposite side, we can also have dark matter that is ultra heavy, which basically is about 10 billion trillion times the proton mass, or even heavier than that. Now we start talking about gram-size particles known as primordial black holes. So how do we go about finding these new particles? There are three, I like to call them 3.5 ways, and I'll explain the half later if you ask me. But there are 3 ways that we try to find these particles. We look for them in the sky, at colliders, and deep underground. And so if we look at the sky, we can look at dense regions like the center of our galaxy, where there's the dark matter density is so high that 2 dark matter particles have a high probability of finding each other and smashing into each other, annihilating into Standard Model particles. Or in principle, you can have dark matter that decays into Standard Model particles. And we can look for these in our telescopes on Earth or in the satellite telescope. So in this case, if dark matter annihilates, it could annihilate into electrons, protons, photons, and neutrinos, which we can look for at telescopes, future telescopes like the Square Kilometre Array, which this is a radio telescope that looks for longer wavelength, shorter, less energetic photons. And when it's built, it's currently being built in Southern Africa. And when it's built, it's going to be the biggest telescope in the world. There's also the Cherenkov Telescope Array, which is looks for much higher energy photons with shorter wavelengths, which we call gamma rays. There's also the neutrino ice cream neutrino observatory, which is in the South Pole, and it looks for these very small, those neutral particles that I mentioned, whose mass we don't know. We don't know where the mass comes from. And so these are some of the ways that we look for these annihilations of dark matter in either at the center of our galaxy or at the center of other galaxies. And there are many other telescopes, by the way, I did not mention over here that we use to look for this type of signal. Another way that we can try to get a handle on this dark matter particle is to try to produce it in our laboratories, like the Large Hadron Collider. So in the Large Hadron Collider, which is the famous collider that we know exists at CERN, is I can accelerate a bunch of protons, inject them into the spring, accelerate one bunch in one direction, accelerate the other bunch in the opposite direction, and have them, as they accelerate, they keep gaining more and more and more speed, they keep getting faster and faster. And then I arrange for them to meet at a specific point. And at that point, I build a very, very large detector. And at this large detector, then I wait for these 2 particles to smash into each other and look for the remnants of stuff that comes out of it. And so energy momentum conservation tells me that the energy that comes in is the energy that comes out. So I know the energy that went in. So if dark matter carries away any energy from this detector, then I would be able to know what energy it carried away and what some of its properties are. So we call this that it carries away some missing energy or missing momentum. So this is one way we try to find dark matter at colliders. And this is a picture of a collider. This is a picture of a detector at CERN. And for scale, this is a human being. And so we saw that we looked for the tiniest particles. We're using the biggest materials or the biggest detectors that we could. So just for that sensitivity, we're really looking for particles that are not that don't interact very strongly with us. In fact, they interact very super weakly with this type of model. Another way that I could do this is to not collide particles together, but to just put a piece of material, and accelerate one particle and hit this material. So we call this a fixed target experiment. And then I can measure what comes out of from this interaction. And so this is one way that we look for lower mass dark matter. So that's sub-GeV class of particles that I mentioned before. So direct detection is a way in this kind of class of detection strategy. We use basically our information of dark matter in our halo. So we know the Milky Way is surrounded by a somewhat spherical halo of dark matter. Now, whether it's really spherical is arguable. Right? So this is a debate. This is something that is still up to investigation, but we think that it's a spherical halo of dark matter. And as the galaxy rotates, we somewhere around here, we keep rotating with this galaxy. And as we keep rotating with it, we keep basically getting hit by this dark matter wind from the halo. And so the sun and the Earth, so the solar system is moving at 220 kilometers around the center of the galaxy. And as we're cruising along, getting hit by this dark matter wind, so all we need to do is nothing sophisticated, just build a huge detector and basically wait for dark matter to come knocking. So we build a big detector, basically wait for dark matter to come and cause a ripple effect. Now, I want to ask a question at this point, and anyone who's brave enough can unmute themselves and answer this question. Why do we put this detector deep underground? I'll pause for a minute to get an answer. No answer? Okay. I will continue. We put basically this detector, we put these detectors deep underground to shield from any radiation that comes, that would be coming from some unknown, known radiation that in the Earth. So for instance, if I was to put this detector on the surface, I'd be getting dark matter hits every few seconds. Because we know actually that there are particles that come from the atmosphere that would enter this detector and mimic a dark matter signal. So we put it deep underground to get natural shielding from the Earth, from the Earth's crust. And we also cover these detectors to get shielding also from the detector material itself. And so basically this is a super quiet environment where we're just waiting for a dark matter particle because it interacts so weak. There's the idea is that it doesn't interact with the rocks and the shielding, but it would have some interaction with some probability of interacting with this material, stellar material that we put in the detector.
Hopi,
yep.
You're at the 41-minute mark.
Okay, I'm almost done. And at this point, if dark matter comes in, hits a nucleus, causes the nucleus to recoil. That recoiling gives off some light or some energy that we detect inside this experiment. And this is one way that we can reconstruct the properties of this incoming dark matter. So I've tried to show you now that we have that dark matter exists, and we have ways of trying to find all that variety of dark matter particles. So what next? We haven't found a signal yet, but our research continues. I mentioned before, we are in a conference where we're discussing dark matter. And in this conference, we've heard about many great ideas of where dark matter, how we can find dark matter, and what it is. And in principle, dark matter may be hiding in plain sight. And we're currently exploring all these new ideas and searches. And in principle, actually, the next decade is a very exciting time in astroparticle physics because there are a range of experiments that are greatly coming online that will allow theorists like me to test our theories of dark matter and possibly, hopefully, find a signal. Now, wrapping up, I hope I've convinced you that finding the nature of dark matter is an urgent problem. It definitely is something that we really feel is really trying hard to find. But there's another urgent problem in physics, which is a problem of diversity, inclusivity, and equity. Now you may ask yourself at this point, well, I'm sorry, what does one have to do with the other? Well, let me put it to you that to fully exploit the diversity of dark matter possibilities, we need diverse minds in this field. And those diverse minds, for that to happen, we need scientists who, from a variety of backgrounds, all of whom are going to feel welcome and supported to do their job. So instead of people worrying about being judged or not feeling supported or being discriminated against, we want people who are going to be working very hard towards this common goal that everyone has, which is to find out. So for instance, so we need people to, as I mentioned, to feel welcome and supported. And for instance, you just listened to a talk about dark matter from a Black man who grew up in a village in South Africa. This would not have happened maybe 10, 20, even 100 years ago, right? And so I want to mention that this is an ongoing problem. We don't have a fix. We don't have a quick fix of this. It's an ongoing problem that is very complex and has many nuances. And in this conference, which is a unique conference and it's one of a kind, we had physicists discussing not only dark matter, but also had invited social scientists and people who are advocates for diversity and inclusivity. Because as physicists, we like to think that we know everything, but we actually don't. So we need people who are actually experts in inclusivity and diversity to come and actually help us and discuss with us some of these problems. And I have to say, this was as a groundbreaking conference that was really important for the advancement of this part of our field. And it hasn't actually been done, at least to my knowledge. And so with this, I would like to thank you for listening to me. And I would like to thank the organizers who are listed here and the Aspen Center for Physics hosts for this wonderful conference. And I want to say that if you want to take your time to really understand what I was talking about and understand it from a minority's perspective, a person who's a minority, I would like to invite you to read this book by Dr. Chandra Prescott-Weinstein. It really is a cool book. Thank you.
Thank you so much, Hopi, and thank you for mentioning my book. But we're here to talk about your ideas. So we have time for questions. I hope everyone, if you want to turn on your cameras, you can maybe give some applause for Hopi before we get started with the questions. Thank you so much. So I see a question from, I'm going to encourage people to use the raise hand feature to just make this a little more orderly for me. So I see a question from Roger Wilson and then from Daniel Silverman. So Roger, go ahead and unmute yourself. Or maybe I have to do it for you. Let's see. Yes.
There we go. Yes, and first of all, thank you. I look forward to more information or more enlightenment from you and from others from Africa and everywhere. You know, it's terrific. I was wondering if there's any measurement, and you may have alluded to this, I'm not sure if I missed it, any measurement of distribution of dark matter through lensing or some other measurement mechanism that is theorized. If so, would that distribution correspond exactly or differentially to visible matter? And what would that tell us?
So if I understand your question exactly, are you asking if gravitational lensing has mapped out some distribution for dark matter, and if this corresponds to visible matter? As to my knowledge, at the scale of galaxy clusters, gravitational lensing doesn't actually give us some sort of give us a global distribution of dark matter. We get kind of a local distribution of dark matter, basically giving us the distribution of dark matter in the specific galaxy cluster. But what gravitational lensing gives us is kind of like the whole picture of the galaxy cluster. But we use other methods to kind of infer the distribution of matter in the galaxy cluster, similar to what we look at in our galaxy.
So the specific sort of narrowed question is there a correspondence, and you may not be able to answer it at this point, between the distribution of dark matter and visible matter at any scale, such that there's an association, or maybe they're totally independent?
They're not actually, it turns out that they're not totally independent. So the distribution that we see actually from that we think that dark matter dark matter and visible matter are kind of also almost distributed the same as through these filamentary structures at the largest scales. So you see these areas of clumpiness. This is where dark matter actually forces all the visible matter to clump up together. And there are regions where basically there's nothing. There's no dark matter, there's no visible matter. And in principle, actually, when I say that there's no dark matter, it's actually not completely correct, because these regions have some amount of dark matter. It's just not as clumpy as in these overlaps.
Okay. Thank you.
All right, next we have a question from Daniel Silverman. And you should be unmuted now.
Yes, I am. Thank you. Thank you, Gopi. I'm not a physicist, and I was able to follow your presentation and understand what you were talking about, which rarely happens when I listen to physicists talking about dark matter, so thank you. And I also want to thank you for putting diversity and inclusion up there as equally important and an equally big challenge and a related challenge. I'm curious if you have any suggestions for action items people can take from outside the community. Is there, are there ways we can put pressure on, I don't know if it's on APA or on the community in general, to deepen their commitment to diversity and inclusion?
This actually, I feel at this point I'm not very equipped to answer this question. I mean, there's people like Chanda who are very well versed on these kind of things and what people can do at that point. But from a non-physicist point of view, the part of the reason I put that there, and part of the reason I actually put this this picture of a diverse group of people, is to basically we should need to change our view of what a physicist looks like. A physicist is not the picture that we used to see about 100 years ago. Members of the LGBTQI community are physicists. People who are with disabilities are physicists. Black women are physicists. White women are physicists. Black men like me are physicists. So changing that narrative basically will allow younger people who are really looking to go into physics to kind of like remove this barrier, remove this kind of curtain that they have, and I know I used to have it. This curtain that's there that, oh well, I don't see anyone like me in that field, so why should I go into that particular field? And basically, I think as members of the public, besides putting pressures on specific organizations, I would say encourage your children, encourage your friends' children, or people of diverse communities to really, if they really want to go into physics, tell them to go. There are now structures that we're putting in place to support everyone into physics. Now, this is a problem that is in its early stages that we're trying to solve, and it's going to take time to solve that. But really, we want more people to come into physics.
All right, and we have a question from Yudai Tsai.
Hi, thanks. Thank you very much for the beautiful talk. I didn't know Queen's University was founded, have this origin that we hardly heard about. And I really want to follow your statement by saying that there are a lot of Black people and Asian people and other people, of course, being attacked right now in North America or other places. And we really would like people to have the support. And I think what Daniel was saying is very great. So it's great to ask what we can do, but it's also important that we think for ourselves what we can help. And I think that would be having a longer lasting impact. One last thing I want to mention is Angelo Quinto. So Angelo Quinto actually is a Filipino person who suffered some kind of police-involved events. I don't want to say too much. You should take a look at that. And his story is much less told. It was told by New York Times, but was never mentioned that he's a Filipino person. So that's something I would like to bring awareness to. Thanks.
Oh, thank you, Eli, for that.
We also have a question from Ning Yuan. I'm gonna unmute you, or are you able to unmute yourself? Okay. Oh, that didn't work for some reason.
Hi, thank you so much for such an interesting talk. I was wondering, near the end, you said that at your conference, you discussed numerous exciting future prospects for detecting dark matter. I was wondering whether you could maybe share with us one or two experiments or directions that you think are the most exciting.
That I think are the most exciting. Well, yeah, I think the direction of, so my interest actually, what I work on currently is looking at this region. I don't know if you can still see my slides. Maybe I can make them a little bit more full screen. Can you still see my slides? Yeah. So I work in this, most in this sub-GeV region and also this ultra-heavy region. So the reason I'm excited about this is that there are a lot of new interesting experiments that are coming up that are looking for dark matter in this particular region of ground space. This includes basically using astrophysics, inference from astrophysics, and as well as using astrophysics to set constraints on some of these particles. And also using direct detection experiments, so like new and upcoming direct detection experiments that specifically are targeted to look in this region of space. And then on this ultra heavy side, basically we can look for new interesting signals of dark matter. So without going into too much detail, so the weakly interacting massive particle paradigm, we built experiments that look for these particles. Unfortunately, we haven't seen anything yet. But what we're actually looking for is that with the assumption that these particles are interacting only once in the detector. And we haven't seen that. But it turns out that if you go to much heavier masses, it is possible that you would actually interact many, many times inside the detector. So these particles may interact much stronger than weakly interacting massive particles. So what we look for in this is a multi-scattering signal, which is a unique signature that we don't even need to build a detector for. The detector is already there. So these are my some of the directions that I'm currently interested in, without going into too much detail about my work. Thank you very much.
Thank you, Ningran, for your question. And I just want to remind people that when you have an opportunity to ask a Black scientist a question, it's great to ask them a question about science. So David Allen, you're next on deck.
Thank you very much. Hi. I understood you to say that dark matter occurred due to at the time of microscopic fluctuations in the Big Bang. Could you please repeat very briefly your explanation for that? That was crucial and I missed that.
Okay, so I kind of skated over this very quickly, but basically this is kind of it kind of goes along with the timeline of the universe. So as we had a Big Bang that gave rise. After the Big Bang happened, the universe was in a state of a very dense, very hot plasma. And as the universe expanded and cooled, this plasma, in this plasma, we could have interactions where dark matter could annihilate into the standard model, and the standard model could annihilate into dark matter. Now, as the universe kept expanding and cooling, the dark matter could annihilate, but the reverse process was not possible anymore. And so as the universe kept expanding and expanding and expanding, we had a process a point whereby we had a kind of a relic or an abundance that was left over from that universe, from the early universe of dark matter. And without going into too much detail, basically we have a period of time where the dark matter clumps up together and forms this filamentary structure that, as the universe expands and cools even more, and we kind of basically zooming into those structures, we see the galaxies and clusters that we see today. I don't know if this answers your question. I don't want to go into too much technical detail.
Well, you gave me a lot of things to try to look up. Thank you very much again for your talk.
Okay, thank you.
Thank you, David. Okay, we're gonna have one more question and then we're gonna wrap up. So the last question goes to Brian Nord. You should unmute yourself, or maybe I have to ask you to.
Okay. Thank you, Chanda. Thank you, Hopi, for this fantastic talk. I learn something every time I listen to you speak. I wonder if you could comment on, AI, artificial intelligence is out there in the world right now, and I'm wondering if you could say a little bit about what you envision as how that might play into some of the science that you talked about tonight.
I think there's a lot of work that has actually been done in terms of artificial intelligence and machine learning to search for signals of dark matter, to kind of distinguish signals of dark matter. And some of my interests, actually, or I haven't really gone down too much into machine learning, but some of my interest is to do kind of so there's this thing called triggering when we look at LHC data. Basically, we have so much data that we isolate the specific process that we're looking for. And so we trigger on a specific analysis or a specific type of signal that we're looking for. Unfortunately, for astronomical data, we cannot do this. Right? You just have a telescope and it just absorbs all your data. So one thing that I'm interested in, or I'm kind of curious about with machine learning is could you have a trigger system? And I know people have actually done this before into astronomy, but I want to think about it from a point of view of signals for dark matter, for instance, for dark matter annihilation. If you have a signal for dark matter annihilation into synchrotron photons at a telescope like the SKA, that's going to take so much data, and basically they have problems with keeping all the data. Could you have a machine learning type of trigger system that allows you to isolate a signal, to basically look for that signal and say, okay, I'm looking only for synchrotron photons, and I'm going to do an analysis on the fly with these synchrotron photons, and maybe we can see a signal of dark matter in this region. But there's so many applications that machine learning and AI could have in this direction. Thank you for the question.
I think everyone joins me in thanking you, Hopi, for that wonderful talk. And thank you, everyone, for joining us this evening. There will be a recording of this available later, I believe. So if you missed anything, please come back, watch it again, check out Hopi's papers, consider inviting him to your institution to come talk to you. And thanks again to the Aspen Center for Physics for hosting this event. Have a good night, everyone.